All right, now this video is a pipe flow system that will require using the Moody diagram in an iterative way to solve what's being asked in the problem statement. So it also has the use of a conservation of momentum, or the momentum equation, the control volume approach. And so it's a nice review as we lead up here to the final exam and finishing this course off. But the question, the system is here. We have a big tank with a pipe coming off of it, where two different pipe sections are being flanged together here. And the question here is, what do the bolts? What is the force in the bolts here to keep this connection if everything is sitting here on a frictionless wheels? Okay. So to start this off, we pick out 3 points in our system, 1, 2, and 3, that are going to be important. And we then take control volume between points 2 and 3 in our system and look at all the forces on this system. These are frictionless wheels here at the bottom, so there's going to be no support being held there in the longitudinal direction here, in the axial direction. But for our momentum, we need to consider both the momentum entering our control volume and the momentum exiting. Well, mass flow rate is going to be equal, and our velocities are going to be equal here. So that the net momentum flux is just 0. The forces that we have are pressure at point 2 here, acting over the area, the cross-sectional area of the pipe, and then that's supported by nothing here at 3 because this is atmospheric pressure. It's a free jet. So this must then be supported by the force of the bolts. So the bolts are now holding on, accounting for this pressure force. And that's what our analysis here shows, direct application of the momentum equation for a control volume. So that the force in the bolts must be equal to the pressure at 2 acting over the area at 2. All right, if we then do the energy equation from 1 to 3 to then relate our dynamical quantities there, we have the pressure head, the velocity head, and the elevation at 1 related to the pressure head, the velocity head, and the elevation at 3. Plus the head loss at 3. Here, pressure at 1 and 3 are both atmospheric, so that cancels out. Our velocity, it's a big tank, so we assume that's pretty close to 0. The elevation change is 3 meters as given in the problem statement. And our velocity at 3 is equal to the velocity that, throughout the entire pipe. So there's a distinction we need to make here. This is the velocity at 3, whereas this is the velocity through the pipe, and they're equal. Okay, so we label them differently, but they are equal. If we solve this for the elevation difference, we know this is 3 meters. What remains unknown here? Well, we don't know F, and we don't know the velocity. We know the geometrical properties and gravity, but we don't know F and V. However, we can relate them using the Moody diagram. Well, this relationship is highly nonlinear, so it's going to require an iterative process to solve it. Okay. So if we then pull the 2g factor over to the left side and multiply it by the 3 meters, we can then get, and then plug everything in, the length and the diameter, we can then get a relationship between f and v squared. An equation, everything is known except f and v, right? We can also, and then we'll call this equation A. We also know the Reynolds number, or also know the form of the Reynolds number, which we need for the Moody diagram, but we still don't know what V is. So we can plug in the diameter and the kinematic viscosity and get a relationship for the Reynolds number in terms of the velocity, but we don't know what the Reynolds number is exactly. So here's a relationship between F and V squared, where also, or F and V through V squared. We also have a relationship between F and V, which is the Moody diagram, which we then need to know what the Reynolds number is. Okay. In the problem statement, it said that we have the piping is galvanized iron. If we go to table 8.1 in your book, look up galvanized iron. We're in the metric system, I believe. So we get a roughness here of 0.15 millimeters. There's our roughness is 0.15 millimeters. Divide that by the diameter to then help us, we'll need this in the Moody diagram. 0.15 over 80 millimeters is our diameter. We get this quantity. So that sets what curve we're going to be on, okay, on the Moody diagram, right? So that tells us which of these families of curves we live on. That's epsilon over d. Reynolds number and friction factor. Again, we don't know Reynolds number. We know it as a function of velocity, and then we can also relate the friction factor through an analytic relationship with the velocity. But this is going to be a nonlinear relationship, so we need to iterate through trial and error. So let's start with assuming a value for the friction factor of 0.02. That's a pretty good choice to always make. It lives kind of at the heart of all the friction factors. We're going to intersect these curves somewhere at some reasonable Reynolds number, so 0.02 is a good place to start. We can then plug this 0.02 into the A relationship to then see what velocity that would be associated with. Solve for velocity, we get 2.6 meters per second. We can then plug this velocity into B to determine what the Reynolds number would be for this friction factor, which would be about 18.8 thousand Reynolds number, or 1.8 times 10, 1.9 about times 10 to the 5. And then we can go to the Moody diagram and then see, with all of this, we assumed f was 0.02. Does Moody diagram say it's 0.02? Again, we're going to now look for the curve that is associated with relative roughness of 0.0019 about, and Reynolds number about 1.9 times 10 to the 5. So roughness curve of about 0.0019 is going to be really close to this 0.002. We then are on this curve here, and looking where that intersects with about 1.9 times 10 to the 5. All right, so a little bit before 2 times 10 to the 5. So the intersection of these two occurs right about, right about there, which is right about at that line. And so if we follow that over, that's the one tick underneath 0.025, which is going to be 0.024. Right, so 0.02, 0.021, 2, 3, 4, 0.024. Okay, well that's close, but it's not a match. So we got a friction factor of 0.024. Doesn't match what we assumed, therefore we need to iterate another time, and let's use this value to iterate on. We then use this value, go through all the same steps again. Assume this friction factor, plug it into A to determine what velocity that would be associated with, plug that velocity into B to determine what the Reynolds number that would be associated with, and then with our epsilon over D of 0.0019, so using the same curve, and now using a Reynolds number of about 17, so 1.7 times 10 to the 5. So we're now even further off of this, kind of right in the middle there. We're a little bit higher than 0.024 now, but we're getting closer, and you could safely assume that the actual friction factor is right around 0.024, maybe 0.0245, but I think we're going to call that good. So our friction factor matches pretty well of about 0.024. And what's going to be important is now we found our velocity, 2.4 meters per second. Now that we found our velocity, again, the goal here, we need to get to the pressure at 2 to then relate to the force in the bolts, the force being held, supported by the bolts. So then we would do the energy equation from 2 to 3 to now relate the pressure at 2, which we need to determine the force in the bolts, to the other quantities that we now know. All right, so if we do the energy equation again, we know that the velocities in this pipe section are all equivalent. Right, we're now dealing everything along here. It's just one uniform diameter pipe. So velocity is all constant at 2.4 meters per second. Elevation doesn't change, and our pressure at 3 is atmospheric. It's a free jet. Pressure at 2 is what we want to know. Our friction factor came from the Moody diagram, with this velocity. And so this reduces to just the pressure at 2 is related to the head loss. Then we can then relate this back to the force in the bolts, which is just the area times the pressure at 2, which then is just the area times the head loss multiplied by the gamma factor. So the gamma over G just goes to the density. Plug all this in with our properties of water and the known quantities, we get a force in the bolts of 88.7 newtons. All right, so that was an example where we had to iterate using the Moody diagram to relate the known quantities to get to the unknown quantity, and it required applying the energy equation twice between two different points twice in the problem solution.